In the present lecture, we are starting with the concept of gravitational field. Now, say we have seen in Newton's law of gravitation, two particles attract each other with a force which is known as gravitational force. Okay, so basically, suppose we have two particles, say m1 and m2. So we have seen they are attracting each other, they are exerting a force on each other which is called the gravitational force. Now see, when we take the model that particles are directly applying the force on each other, such a model is called action at a distance model. Action at a distance model. Okay, now see, in action at a distance model, what happens? One particle transmits the force instantaneously to another particle. Okay, whenever the particles are operating through action at a distance mode, it means there is no time taken by the force to be transmitted from one particle to another particle. So according to this model, the force is transmitted instantly. The force is transmitted instantly between the particles. Okay, there is no intermediate agent, there is nothing to play the role of any intermediate agent. Okay, the particles are interacting directly with each other, transmitting the force instantly without any time delay. Such a model is called action at a distance model. Now another model for the interaction of the particle is the field model. This is one of the model which is called action at a distance model. Now we have another model which is called the field model. We have the theory of field. Now what is the field theory? We have an intermediate agent. We have an intermediate agent between the particles which is called the field. Okay, so basically what happens, any one of the particle modify the space around it. Any one of the particle modifies the space around it, creating the gravitational field, and this field exerts the gravitational force on any other particle which is brought in this field. So basically in this case, mass interact with another mass through an intermediate agent which is known as field. And you know, same thing will happen with the electric charges. When you will study electrostatics, you can visualize the force between two charges through action at a distance model, in which the two charges would be attracting or repelling directly with each other without any time delay, transmitting the force instantly. Or through the field model, in which one of the charges will create the field and this field will exert a force on another charge. So in the field model, what is happening, you know, when we have any one of the mass, it creates a region of influence around itself. It modifies the space around itself, and this region of influence is called gravitational field. Okay, this region of influence is called gravitational field, and it is a vector field. At each point it will have the magnitude as well as the direction, so we denote it by vector g. Now if you bring any other mass, in this region of influence, this is say another mass, so basically this gravitational field applies a gravitational force on this another mass. So in the field model, the particles are not directly interacting with each other. Are you getting the point? In the field model, the particles are not directly interacting with each other. They are interacting with each other through an intermediate agent which is called the field. Now, field is a microscopic property. What it means, it may change from one point to another point. So whenever you want to find the field, you have to be very much clear at which point you are finding the field. Okay, suppose we are finding the field at this point of space, then you are very much clear that the target point is this particular point in space. We are going to find the gravitational field at this particular point. So field is a microscopic property. Field is a microscopic property. It means it is the property of a point in space. It means it is the property of a point in space. Okay, it may change from one point to another point, and also it may change with time. Okay, we have seen in the fundamentals of types of field that field may be uniform or non-uniform, field may be static or time varying. So it is possible that at a particular point the field may be changing with time. Such a field is called time varying field. If the field remains constant with time, such a field is called static field. Okay, so basically it is the combined property of space and time. It may change from one point to another point, and it may also change at a particular point with time. Got it? Now same, if you want to find the gravitational field at any point, so basically there are two, you can classify the masses as one of the mass which is creating the field, which will be called the source mass. Okay, and one of the masses which will test the presence of the field. This is called the test mass. So when we talk about test mass, say m naught, so test mass is simply for detecting and measuring the gravitational field. Now you know field is the property of a point in space, and there must be some source. There must be some source which creates that gravitational field. Suppose we have a planet, okay, and the ball is falling towards the planet. Now see, you can visualize this scenario in two different ways. You can say the planet is exerting gravitational force on ball. Okay, now you are not taking the name of the field, you are not involving any intermediate agent, you are just talking in sense of the action at a distance scenario, that planet is exerting some gravitational force on the ball. It is simply the interaction between the planet and the ball. There is no role of any intermediate agent. Now in an alternative way, you can say the gravitational field of the planet, exerts a gravitational force on ball. This is what? The field theory. Now see, in this scenario, what you are going to do, you are giving the accountability of the force on the ball not to the planet but to the field of the planet. Are you getting the difference? Here you are saying there is no field. Planet itself is exerting the force on the ball. This is the action at a distance concept. And in this case you are saying the planet is creating some region of influence. The planet is modifying the space around itself, setting up a gravitational field, and then that gravitational field would be exerting the gravitational force on the ball. Okay, so both the explanation are equivalent. The difference is here you are explaining it with the action at a distance theory, here you are explaining it with the field theory. So see, as we have seen, test mass is the mass which is used to determine how much field is existing at any point. Now let's see, when we say what is the field at any point. So the field at any point will depend on the source, because who creates the gravitational field? Just think for 1 minute. What may be the source of gravitational field? So it must be some mass. The mass may be the planet, the mass may be a stone, the mass may be the sun, the mass may be the moon. Every mass, whether small or big, will be creating a gravitational field around itself. Again I repeat, any massive object, massive means an object which has a mass, any massive object creates a gravitational field around itself. Okay, so the mass which creates the gravitational field, whose field you are going to find, is called the source mass. Okay, that is called the source mass. Suppose you have a planet and at a point P or at a point Q or at a point R, you are finding the gravitational field of the planet. Of course, the planet would be creating the gravitational field around itself. So basically you are finding the gravitational field of the planet, and in this case, what is the source mass? The source mass is the planet, yes or no? Because it is the planet which is responsible for this field which you want to calculate. So at any point whenever you are finding the field, the role of the test mass is limited. Again I repeat, it is very conceptual point. The role of the test mass is limited. The test mass will only detect and measure the field. It can never create or change the field. Remember, the test mass will never create or change the field. It is only going to detect the field and measure the field which has already been in existence. You are not going to create anything new. You are just going to discover something which has already been existing. Suppose you want to know the gravitational field of the planet Earth at the surface of the planet, and say it is 9.8 meter per second square vertically downwards. So it is the gravitational field in existence, and if you are bringing some test mass to measure this field, so the test mass will not change this field. The test mass will only measure the value of the existing field, that is 9.8 meter per second square. So let's see how we define the gravitational field at any point. If you want to find the gravitational field at any point, gravitational field at any point, of course in space you are talking any point. So suppose there is a point P, and at a point P you have to find a gravitational field. We have to find a gravitational field at a point P, and for finding the gravitational field you have to bring some particle. To say a particle of mass m0 is kept at P. Okay, for finding the field you bring a particle of mass m0. You know what is the name of such mass? What name it is given? It is the test mass. Remember, it is going to detect and measure the field. So at P you have kept a mass m0. Now measure the gravitational force on m0. Measure not any other kind of forces, and also not the net force. We are, for finding the gravitational field, we simply need to measure the gravitational force. Okay, maybe some other forces too are acting on the particle, maybe the resultant force on the particle be 0. We are not concerned about these things. We have to find only the gravitational force. Measure the gravitational force on m0. Of course, who is going to exert this gravitational force on m0, and whether gravitational force will be exerted or not? There are two main points: whether the gravitational force will be exerted on m0 or not, because as I told you, we are not interested in other kinds of forces. Maybe there are a lot of other forces acting on m0, electromagnetic force, any other force exerted by fluid. We are mainly interested in the gravitational force. So first primary question is ki whether gravitational force will be exerted or not, and number two, if it is exerted, then who is exerting this gravitational force? So if there is some gravitational field at a point P, if there is some existing gravitational field, then only some gravitational force would be exerted on m0. If there is no field at P, then no gravitational force will be exerted on m0. Okay, so basically if there is some gravitational field at P, then only gravitational force will be exerted on m naught. So if you measure some gravitational force on m naught, when you are keeping m naught at P, and if you detect some gravitational force on m naught, then you can be sure that there is an existence of gravitational field at P. You can be 100% sure that there must be some existing field at P, because only gravitational field can exert a force on m naught. Now we have to define operationally, we have to give some mathematical model definition to what would be the magnitude and direction of the field at P, because gravitational field is a vector quantity. So we have to devise some way, some definition ki how you are going to define the field at P. So suppose the gravitational force acting on m naught is Fg. So the field at any point is defined as the gravitational force acting per unit test mass, that is Fg divided by m naught. See, this is how you define the gravitational field at any point. The gravitational force acting per unit test mass. So suppose in your room, say right in front of your nose, if you have to find what is the gravitational field at this particular point, bring a particle of mass m naught, keep the particle m naught at this point, measure the gravitational force on m naught, and then divide this gravitational force by m naught. If you want to see what will be the magnitude of G, so when you write the magnitude, you can write like G or vector G in modulus, and this will be the magnitude of the gravitational force divided by m naught. And if you want to see what will be the SI unit, so you can see it will be Newton per kg, force is in Newton, mass in kg, and this can also be written like meter per second square, right? Same as the unit of acceleration, force by mass. Now tell me one thing, as I told you, the role of m naught is simply to detect the field. If you are changing m naught, suppose you are changing m naught, what do you think? Will there be any change in the field? This is very conceptual point. Suppose at a point P, you have to find what is the gravitational field, okay? And you bring a mass of m naught, say 5 kg, and you kept this m naught 5 kg at a point P, and then you measure the gravitational force, and the gravitational force comes to be say 20 newtons downwards. So you'll say the gravitational, because you see in this case the direction of the, it is a vector equation, so the direction of vector G will be same as the direction of the gravitational force. So you'll say the gravitational field at P will be vertically downward. Surely it will be vertically downward because Fg is acting vertically downward. If Fg is acting vertically downward, field will also be vertically downward, okay? And what will be the magnitude of gravitational field? You will say the gravitational force divided by m naught. So you'll get 20 newtons divided by 5 kg. So you'll get 4 newton per kg, or you can say 4 meter per second square, okay? Now it means at a point P, now you can remove m naught. Now what will be the field at P? So at a point P, you will say the gravitational field is present with a value of 4 meter per second square, okay? Now my point is that you have measured the field at P with the help of m naught. For measuring the field at P, you brought a particle of mass 5 kg m naught. Now what will be the field at P if I remove the particle from P? Suppose if nothing is kept at P now, nothing is kept at P now, then what will be the field at P? If m naught is removed, that is now no mass is kept at P, then what will be field at P? Now can you tell the answer? With the help of m naught, you found the field at P. Now you have thrown out m naught, there is nothing at P. So what do you think? Just think for 1 minute. What do you think if I am keeping nothing at P now? What will be the field at P? Well, the answer will be the same. That is 4 meter per second square vertically downward. This is very beautiful and conceptual point. The field at P, whether you are keeping m naught or not, will be the same. That is 4 meter per second square, which you discovered with the help of m naught. Again, I remind you, the role of m naught is simply to find some existing field. M naught has no role in creating the field. M naught is simply helping you to find which is something already existing. So the field was already in existence, and m naught played the role to detect that field and to measure that field. So even if you are removing m naught, the field would be what? 4 meter per second square. And this would have been the field even before bringing m naught. Are you getting the point? This would have been the field even when m naught was not there. The role of m naught was to measure this field which was unknown to you. So there will be no change in the field because field is due to some source. And what is the source of the field? That is not specified here. Neither we are going right now into that detail because of which source this field is present. The point is that here, the point which I want to drive home is that m naught is simply for detecting and measuring the field and not for creating the field. So the field is because of some other source, which of course is not specified in the present problem. This field is this field must be due to some source mass, okay, like the planet or the ring or the sun, anything like that. Source mass which is not specified. There is no role of m naught in creating this field, okay. So if you change m naught, there will be no change in small g. Of course, the force will change. Are you getting the point? If you are changing m naught, the force will change, but there will be no change in the value of small g. So on changing m naught, of course the gravitational force will change, but the gravitational field at P will remain the same, okay. Got it? Because the field is not because of m naught, the field is due to some other source. And if you make the equation, in this equation, see vector g is fg divided by m naught. If you make fg as the subject, it will come to be m naught multiplied by g. Now what this equation is telling you, whenever you keep some particle in the gravitational field, the field will exert a gravitational force on the particle, and the direction of the force, gravitational force, will be same as the direction of the gravitational field. Suppose this is the gravitational field and you are keeping a particle m naught in this gravitational field, so this field will exert a gravitational force on m naught, fg. And if you want to write simply the magnitude of fg, it will be m naught multiplied by the magnitude of g. We are not putting the vector sign because we are simply writing the magnitude, okay. And what do you think? Is this g, the gravitational force, due to m naught? Because every mass will create a field, so m naught will also create its own gravitational field. But this g, which is exerting the force on m naught, is not the field of m naught. Remember, a particle's own gravitational field will not exert the force on that particle. So in this case, g is not the field due to m naught. Okay, it is due to some other source. We are not going into the detail of that source, like Earth has a gravitational field 9.8 near its surface. So that G is because of the planet, and if you leave anything in that field, that particular field will exert a gravitational force on that particle. Okay, so if you are changing m naught, every time the force will change, but G will not change. Can you convince yourself? For example, if you see the planet, say you are standing near the planet surface, and you say the gravitational field of the planet is, we are talking about Earth, is downwards, and this is how much? 9.8 meter per second square. So according to this property, if you put any particle of mass m naught, then this field will exert a gravitational force on m naught Fg. Of course, where? In the direction of the field, that is vertically downward, and Fg will have a magnitude m naught G, say. So if you are changing m naught, if you change m naught, so what will happen? The gravitational force will change, but G will remain the same, because G is not because of m naught, G is due to planet. Are you getting the point? M naught has no role in G. Small g is due to the planet, so G will remain the same. So if you put a mass of say 1 kg, then the gravitational force will be 9.8 Newton. If you put a mass of say 2 kg, then the gravitational force will be 19.6 Newton. So each time you see the gravitational force is changing, but G will remain the same in each case, 9.8 meter per second square. Okay, got it? So always remember, whenever you're finding the gravitational field at any point, because of the test mass m naught, the role of the test mass is limited only for finding the gravitational field, not creating or changing the gravitational field. And also, you know, ideally when we measure, not calculate, because when you are calculating you are not doing any actual experiment. So when we measure, so in the defining equation we write like this: the gravitational field at any point is limit m naught ideally approaches 0, the gravitational force divided by m naught. Of course, we are not never going to use this equation in calculation. This is for the definition of the gravitational field. What it reflects that for finding the gravitational field, ideally m naught will have a 0 value. Why? Because you see, suppose you want to measure the gravitational field of the planet, and planet has some particular value of gravitational field near its surface, say 9.8 meter per second square. And for measuring this field, you bring a test mass, and if the test mass is very massive, very much massive, very large mass, then it will create its own field which will interfere with the field of the planet. So your measurement will have a high scope of error. So for high accuracy, we want this interference to be minimized. We don't want the gravitational field of m naught to be very large. So for that sense, we will keep m naught very small. So ideally, we will write the equation like this. But for measurement, as I told you, we will always write like this. Okay? And if you want to find the magnitude, it will be Fg by m naught. So suppose if I give you one problem that to measure the gravitational field at P, to measure the gravitational field at P, a test mass m naught is 2 kg is kept at P. It is acted upon by a gravitational force 10 Newton northeast. Okay? So what will be the field at what will be gravitational field at P? Okay, now see the first part. You have to find what will be the gravitational field at P. So suppose I am making the direction grid. north, south, west, east, and this is a point P, and you are keeping a particle of mass 2 kg at P, and when you are keeping a particle of mass 2 kg, it experiences a gravitational force northeast. So if there is a gravitational force, it means there is gravitational field, and we have seen the direction of the gravitational field is same as the direction of the gravitational force. So the gravitational field will be northeast, and how much? Gravitational force divided by m naught. So I'll get how much gravitational force? 10 Newton by 2 kg, that is 5 Newton per kg, or you can say 5 meter per second square. And is there any role of m naught in setting up this field? No. Already we have seen in much detail. So even if you remove m naught, there is no m naught. You can say at a point P we have a gravitational field northeast. How much? 5 meter per second square. Okay. Now suppose in the second part we have been told now a mass of say 4 kg is kept at P, then what will be gravitational field at P, and what will be gravitational force at P. Now what you want to do, you have replaced the 2 kg mass with a mass of 4 kg. Now you are bringing a mass of 4 kg and keeping it at P. So what do you think? If you are replacing the particle which has been kept at P to measure the field, if you are changing that, will there be any change in the gravitational field? Do you think there is any change in the gravitational field? No. The gravitational field will remain the same, because there is no role of that particle in the gravitational field, so it would remain the same, 5 meter per second square. But the force will change. What will be the direction of the new gravitational force? Of course, in the direction of the gravitational field, Fg. So the force will change, because the force will depend on the particle which is kept at P, and the formula for force is mass kept at P into G. So the force will be 4 kg into 5 meter per second square, that is how much? 20 Newton. So now I guess it must be very much clear to you, because these points are very important. Not only these are going to be applied in gravitation, but also they will have the same approach, same application in electrostatics. Number one, field is the property of a point in space. Number two, field is due to some source mass. Until you are changing that source mass, there will be no change in the field. Number three, the test mass is a mass which is intended or used to measure the field, to detect the field. If you change the test mass, there will be no change in the field. Number four, if you change the test mass, the gravitational force on test mass will change. Like in this case, every time when you are changing m naught, each time Fg will change, but the gravitational field will remain the same. Okay.